Okay, now let's define d from EPQR to EP minus R plus 1, comma, Q plus R sub R. This will be a map between two quotients. We will start by defining a map between XPQR and X minus R plus 1, comma, Q plus R sub R. Okay, so we define a D pre sub R. We first take an element from this XPQR. By definition, it is the leading term of some S sub X. This S sub X, by the definition of XPQR, is an element in SPQR. Now, we send this S sub X by D to D S sub X. By definition of SPQR, D of S sub X is an element in S P minus R plus 1 Q minus R sub R. Oops, no sub R for this moment. So D sends elements in here to here by definition of R closed PQ strips. Okay, now let's take the leading term of this ds sub x, and we will get some element y in here. Sorry, we don't know if y is in here for this moment. Let's erase this. We actually want to prove y is really an element in here. To this end, we recall the lemma. Any closed PQ strip is a R closed for all R. The lemma tells us, since this ds sub x is closed because d square is 0, it is actually R closed for any R. So ds sub x is actually in Sp minus R plus 1, comma, Q minus R sub R. So now, by the definition of this guy, y is really a well-defined element in here. However, this D pre sub R is not necessarily a map. It's not well-defined because there can be many liftings of this X. To make it well-defined, we have to do one step further. We will change this map by changing its codomain first. We will change its codomain to make it smaller. Now we take the quotient of this guy modulo y sup p minus r plus 1, comma, q plus r sub r. And also this definition needs to be changed. It will be the equivalence class this y is living in. Now this d pre sub r should be well defined. And let's prove it. Suppose that y is the leading term of ds sub x, and y prime is the leading term of ds prime sub x. Then it follows that the difference of them is the leading term of the difference of s sub x and s prime sub x. To prove that d pre sub r is independent of the choice of s sub x, we must show that y and y prime are in the same equivalence class. In other words, the difference y minus y prime must live in this guy. So we need to show that y minus y prime is the element of y superscript p minus r plus 1, q plus r sub r. Now by definition of this guy, we must show, and suffices to show, we have to be very careful in here. So let's first recall what is the definition of y. So here's the definition of y. And here we are going to replace p by p minus r plus 1 and q by q plus r. Okay, so those superscripts are also have to be changed. We need to replace this p by p minus r plus 1. So this part will become p minus 1. And how about this part? We replace q by q plus r. So this part will become q plus 1. Okay, so this is the definition of y p minus r plus 1 q plus r sub r. Now, to show that y minus y prime is in here, it suffices to show that d of s sub x minus s prime sub x is in here. And now it suffices to show that s sub x minus s prime sub x is in here, is in s superscript p minus 1, q plus 1 sub r minus 1. Okay, so why is this true? In order to prove this, let's draw a picture. Okay, now both s sub x and s prime sub x are PQ strips. PQ strips, but they have the same leading term in here. So s sub x minus s prime sub x must be a p minus 1, q plus 1 strip, because s sub x and s prime sub x have the same leading term. Now, why are they r minus 1 closed? This is because if you regard s sub x and s prime sub x are r-closed PQ strip, their difference must also be a r-closed PQ strip. In this figure, it means s sub x and minus s prime sub x can be norked r terms deep into this filtration. Say this guy vanishes, and this guy vanishes, and this guy vanishes. However, for s sub x minus s prime sub x, this PQ term is already 0. If we regard s sub x minus s prime sub x as a p minus 1 q plus 1 strip, then as an element in here, this difference will only be knocked r minus 1 terms, starting from here, 1, 2. Originally it is knocked into the filtration by 3 terms, 1, 2, 3. But now, if the leading term is this guy, only 2 terms will vanish after applying the differential. So therefore, s sub x minus s prime sub x is R-1 closed. As a PQ strip, they are R-closed, and as a P-1 Q plus 1 strip, they are R-1 closed, because this term will not be counted. Now we have proved the well-definedness of this D pre sub R. Now in order to prove that D pre sub R induces D sub R from this quotient, we must show D pre sub R Q's YPQ sub R. Now let's show this. So now let's take an element X from this YPQ sub R. Then X will be the leading term of some D of S sub X, where S sub X is R-1 strip. It's very complicated. Now by definition, we can first lift X to ds sub X. Notice that the D pre sub R is independent of our lifting. We send this D of S sub X to dd S sub X, which is 0 because dd is 0, and send it back to an element here. But it should also be 0 because this term, whole term is 0. Its leading term must also be 0. Therefore, D pre sub R Q's YPQ sub R. So it follows that this D pre sub R induces a morphism between two quotients and is well defined. This completes the construction of D sub R. And D sub R square is 0 because this D square is 0 and D sub R is induced by D. So D sub R is a morphism in the complex.